Imagine a 300-ton steel giant hurtling toward the runway at 200 miles per hour. The moment those wheels touch the tarmac, they don't just roll. They undergo an instantaneous, violent acceleration from 0 to thousands of RPM, absorbing the force of an earthquake in a fraction of a second. You probably look at a plane and think about the engines, but those aren't the parts that save lives during the most critical moments of flight. It's the tires, standing as a final barrier between a controlled landing and a catastrophic disaster. But here's what nobody tells you. These aren't just rubber circles. They are hyper-engineered pressure vessels, and we're going to take you deep inside the secret factories where they're born. Most people assume these are made of standard rubber, but that couldn't be further from the truth. This process begins in the lush plantations of Southeast Asia, specifically Thailand and Indonesia, where natural rubber is harvested as liquid latex from the Hevea brasiliensis tree. This raw sap, refined to a 99.9% purity level, is then transported thousands of miles to specialized compounding facilities. It is mixed with carbon black, mined from high-grade petroleum coke, and a complex cocktail of sulfur, antioxidants, and anti-ozonants that you won't find in any consumer car tire. What happens next is a meticulous balancing act of chemistry that would put a pharmaceutical lab to shame. But the real mystery begins when we start building the skeleton of the tire itself. You might think the strength comes from the rubber, but you'd be wrong. The true hero is the nylon cord fabric. This isn't your average fabric. These are aerospace-grade, high-tensile nylon filaments manufactured in top-tier facilities in Japan and the United States. We take these thin, nearly invisible threads and weave them into a heavy-duty fabric that is then dipped in proprietary adhesive solution to ensure the rubber bonds to it at a molecular level. It is a grueling, invisible process. If the bond strength is off by even a fraction of a percent, the tire will delaminate under the heat of a 400-mile-per-hour touchdown. And just when you think the foundation is solid, the factory floor shifts into a phase of assembly that pushes the boundaries of human precision. Now, watch as the tire builder, a skilled technician working in tandem with a robotic drum, layers these components with surgical accuracy. The drum spins at a precise speed of 60 revolutions per minute as the technician lays down the bead bundles, which are high-strength steel wires that give the tire its structure. We apply the rubber compounds in layers, each one heated to exactly 65 degrees Celsius to ensure tackiness. The air in this room is thick with the smell of sulfur and vulcanized rubber, a heavy, pungent scent that signals the birth of a tire. Every square millimeter of the rubber is checked for air pockets because, in the thin air at 30,000 feet, a single bubble can expand and tear the tire apart from the inside out. Once the green tire, the raw, unvulcanized version, is finished, it moves to the curing press, the heart of the factory. This is where the magic happens, but it's a process of absolute intensity. The tire is placed into a metal mold, and for the next 45 minutes, it is subjected to 175 degrees Celsius of heat and a staggering pressure of 300 psi. The chemical reaction of vulcanization takes place, cross-linking the polymer chains of the rubber into a singular, indestructible mass. It is a loud, rhythmic environment, filled with the hiss of steam and the deep, booming thuds of hydraulic presses closing. If the temperature drops by even 2 degrees, the internal structure won't solidify correctly, and we have to scrap a product worth more than a luxury sedan. After the tire is cured, it enters the testing phase, where it's pushed far beyond the limits it will ever face in the real world. We use high-speed AI vision systems that scan the tire at a resolution of 10 microns, searching for internal fissures that the human eye could never detect. Then we simulate a landing. A massive vertical test rig drops a weighted carriage onto the tire at a simulated descent speed of 250 miles per hour. The sound is a deafening, bone-shaking crash that reverberates through the entire facility. We are looking for failure, but we rarely find it. The tolerance for error here is essentially zero, because on the runway, there is no second chance. Globally, the market for these specialized tires is surprisingly small but incredibly high value, worth over $1.5 billion annually. The production is dominated by giants like Michelin, Bridgestone, and Goodyear, with factories concentrated in North America, France, and Japan. Despite decades of aviation history, we are seeing a massive shift in materials. We are now experimenting with self-healing polymers and synthetic fibers that can withstand temperatures of over 300 degrees Celsius. There are fewer than 10,000 workers worldwide certified to manufacture these critical components. The industry is currently shifting toward 100% automation for the curing process, reducing human interaction to decrease the risk of contamination to a near 0%. Did you know that an aircraft tire is actually designed to be recapped or retreaded up to 10 times before it is permanently retired? Another shocker. These tires are filled with nitrogen rather than regular air, because moisture in regular air can cause a tire to explode when it heats up during braking. And perhaps the most surprising fact of all is that a single aircraft tire can support a load of over 60,000 pounds, yet it's only about 4 inches thick at its strongest point. It is a masterpiece of material science, designed to endure the most extreme transition from a freezing cold of the upper atmosphere to the scorching heat of a runway in a matter of minutes. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.